Welcome to Calculus. Today we'll investigate solving related rates problems involving right triangles. We'll take a look at two examples. Here's our first example. It's about a 5-foot ladder leaning against a wall and sliding towards the floor. The foot of the ladder is sliding away from the base of the wall at a rate of 4 feet per second. How fast is the top of the ladder sliding down the wall when the top of the ladder is 4 feet from the ground? I would start by drawing a diagram of the situation. We've got a wall, a floor, and leaning against the wall with its foot on the floor is a ladder. So within that situation, what I can identify geometrically is a right triangle. And I see that right angle where the wall meets the floor. Now, because this is a related rates problem, what I want to start with is identification of my variables. So what I see here is that I've got some height on the wall that is forming one of the legs of the right triangle. I also have this length along the floor that's the other leg. So definitely my two variables involve the height of the wall and also the length of the floor. So remember, when we're doing a related rates problem, at that point I want to consider what rates am I interested in within those type measurements. So before I head to do that, let me, well, we'll do that first. So I'm going to look first and say, definitely the height is changing as that ladder slides down the wall. And that is what we want to know. That's really the question. And it's right here. How fast is the top of the ladder sliding down the wall? We also have the rate dl dt. And that's the rate at which the length between the wall and the foot of the ladder on the floor, how is that increasing? We're actually told that that's increasing at a constant rate of 4 feet per second. So then once I've got my variables and my rates there, I want to notice if I've got any particular information. So definitely I'm told that the instant when I'm trying to find this specific dH dt, the change of the height on the wall as time progresses, that I'm looking at that when the top of the ladder is 4 feet from the ground. So that's going to be an H value of 4. So as I come over to my triangle, what I want to notice is that I do know the length of the ladder. That's the hypotenuse of that right triangle. That's 5 feet. Now, if I take my specific height, which I just marked at 4 feet, so that's the height we're interested in to find the rate of the height's change, that allows me to solve for L as well. And I can see that this is one of those special right triangles that has integer lengths. That's a 3, 4, 5 right triangle. So I could confirm that with Pythagorean theorem. 3 squared is 9 plus 4 squared, 16, is 25, and that's equal to 5 squared. All that's left for us to do here is to create an equation that relates these two variables, the height of the wall and the length of the floor. Well, since they're within a right triangle arrangement, we can use the Pythagorean theorem. So the way that I'm going to write it is h squared, so that's the length of the upper leg squared, plus the length squared equals 5 squared, because that ladder is not going to change its length. It's always going to be 5 squared. So at this point, I want to go ahead and take the derivative of both sides. So I'm going to apply ddt to each term in the equation. And what that'll give me is this differentiated equation. So it's going to be 2h dH dt plus 2L dl dt, and that's going to equal 0. The derivative of 25 would be 0. So once I've taken the derivative, it's just up to me to substitute in information and then solve for the rate that I'm looking for. I'm looking for dH dt. So I'm going to go ahead and highlight that here in green. So the stuff around it, I need to plug in information. I also need to solve then for dH dt. So let's do the substitutions first. So I know that the height there, we'd already solved and labeled our right triangle over there is going to be 4. So we'll have 2 times 4 times dH dt. Again, that's what I'm looking for, dH dt. So I'm going to leave it as a variable. Plus 2 times the length. We had solved the length in this triangle to be 3 feet. And then dl dt we know is going to be 4 feet per second. And this is all from the information that we had gathered from the situation. 4 feet per second. And I should probably put the units on the 4. So now what we need to do once I've substituted that information in is I need to reduce and then solve for dH dt. So I see with this term here, 2 times 3 times 4, that's going to multiply out to 24 feet squared per second. So then I've got 8 feet times dH dt as the second term there. And the operation between is plus. So at that point, I just need to subtract 24 and divide by 8. And what that's going to give me is dH dt equals -3. And my feet are going to cancel one with the other. So feet squared divided by feet is just going to be feet per second. And if we were to interpret that in the situation, that means that the height of the wall between the floor and the top of the ladder is decreasing at a rate of -3 feet per second when the height of that wall is 4 feet. Let's take a look at a second situation that also involves a right triangle. So this is about an observer that stands 600 feet away from a launch pad to observe a rocket launch. The rocket blasts off and maintains a velocity of 800 feet per second. Assume the scenario can be modeled as a right triangle. How fast is the observer to rocket distance changing when the rocket is 800 feet from the ground? So just creating a diagram of this scenario, we've got an observer that's standing 600 feet away from a launch pad. So the launch pad's indicated there at the vertex of this angle there. And a rocket is launching from the launch pad upwards, directly vertically. So we'll just sketch in our rocket. So it's definitely on the move. It's not a static object. And we're told that its velocity is 800 feet per second. So it's really hustling. 800 feet per second. Now, we're interested in this distance between the observer and the rocket ship. That's really, if we think about that right triangle, the hypotenuse. So when we think about the variables that are involved in this related rate situation, I definitely have the height of this rocket off the ground, and that's going to be one of the legs of this right triangle. The other leg which is the distance from the launch pad back to the observer, that's fixed at 600 feet. Now we are really interested in this hypotenuse, so that's that observer to rocket distance, and the way we'll label that is as C, since in a right triangle that side would be the C side. So let's just pull our variables from that situation. So I've got an H, that's the height of the rocket, and I've also got a C, which is the distance from the observer to the rocket. That's that hypotenuse, observer to rocket distance. So as I think then about my rates that are involved in the situation, I definitely have a dH, dt, so the change of the rocket as time passes, and that I know, that's the velocity of the rocket. That's 800 feet per second. And what I'm looking for is dc dt. How is the rate of change of that distance from the observer to the rocket changing, specifically when the rocket is 800 feet from the ground? So that's that third piece of information, the specific data that I can pull. At the height is 800 feet. So I will label that over here on our diagram as well, that we're really interested in the moment when the rocket is 800 feet above the launch pad. If we use the idea of right triangles and Pythagorean triples again, I see that this is another version of the 3, 4, 5 right triangle. I've got 3 times 200 would give me 600, and 4 times 200 will give me 800. So I can just extrapolate that this C side is going to be 5 times 200, which is 1,000. So we'll consider that our C value is 1,000 feet when I've got the legs at 600 feet and 800 feet. Okay, so we're ready to come up with an equation that will relate the height and the observer to rocket distance. And again, we can use the Pythagorean theorem because the geometric situation is a right triangle. So the way that we'll set it up is 600 feet. That's that fixed distance from the launch pad to the observer squared, that's a leg, plus h squared, so that's the other leg, the height. And I'm leaving that as a variable because it's changing. It's the height of the rocket as it's taking off equals c squared. So at that point, I've got a good relationship between my two variables, and to find the rates that are involved, I'm going to take the derivative of the entire equation. So I'll apply the derivative to each term here. So the derivative of 600 feet squared, 360,000 feet squared is going to be 0. Plus 2h dH dt equals 2c dc dt. And that equation is now ready for me to substitute information and then solve for the rate that I'm looking for. And the rate that I'm looking for, again, is this dc dt. That's the one that I don't know. So we'll start to substitute. I'll let that 0 fade away. 2 times the height. The height that we saw specifically here was going to be 800 feet. And dH dt we know is also 800 feet per second. And all that equals 2 times the length of the observer to rocket distance when the height is 800, so that's going to be 1,000 feet times what I'm looking for, dc dt. Everything's substituted in. At this point, I just need to solve it for dc dt. So what I see here is I've got a 2 on each side of the equation that can cancel by division. I've got 1,000 on this right side. If I divide this left side by 1,000, it's going to take away 3 of these zeros. And what that tells me is dc dt equals 8 feet per second times 80 feet. And I've got to also think I've divided by feet, so that's actually going to cancel the feet variable. So that ends up giving me 640 feet per second. And that should be the rate of change of that observer to rocket distance when the height of the rocket's 800 feet. Well, thank you for joining for this investigation of related rates problems involving right triangles. See you soon.